Thank you. Heavenly Father, we thank you for the weekend and for rest. Just pray you be with us today. Help us to understand what we're going over. I just pray you encourage the students to work on this class and their others as the semester goes on, that you be glorified, Lord, and we do. In your name I pray, Lord Jesus. Amen. All right. So let me dive back into basically here's the claim is as follows. F holomorphic on, a domain, let's say D, Z in the complex is such that the modulus of Z minus Z naught is less than rho, implies that F is analytic on Z minus Z minus Z naught. Let's see here. Let's think carefully. Well, it's analytic on D, let's say, and the radius of convergence for the series representation of f of z. In other words, f of z is equal to a sum a sub k z minus z naught to the k equals 0 to infinity, has radius of convergence r, which is greater than or equal to rho. Okay. So it's not that like it's analytic on some subset of the disk on which it's holomorphic. It's analytic on the whole disk, and at least that much, maybe more. All right. So for example, if there's even one point on the circle of radius radius rho centered at z naught on which f is not holomorphic, that spoils it. You can't find a power series. Well, at least this theorem doesn't say you can. No, I'm pretty sure you can't, because then, no, you can't. You can't. Okay, so the proof is actually kind of interesting and more or less computational. In my notes, I first do it for z naught equal to 0, then I do it for z equal to z naught. I'm just going to go ahead and do the proof at z naught for you guys. So let's suppose that we have z minus z naught less than r, which is less than rho. So look at some radius less than rho. And the w minus z naught is equal to r. So w is a point on the circle of radius r centered at z naught. Then what do we have? We have z minus z naught less than w modulus of w minus z naught, right? I'm just going to go ahead and address this inequality at the start of the argument so we have it in hand to work with. What's this imply then? Z minus z naught, right? Divided by w minus w naught, w minus z naught rather, is less than what? This is not rocket science. Why is rocket science the go-to for a complicated thing, by the way? Why not say, yeah, this isn't home cooking, right? Very good, Sharon. I mean, admittedly, home cooking for 6 children is challenging. So I see how you're making comments about your future. I get it. But I think we should put a 1 here, right? No? Children are a blessing. What's your problem, people? So are cats are not a blessing. There's no scriptural basis for that. I don't think. I mean, the lion laying down with the lamb. It's not like oh, that's a normal thing. It's like, that is so epic, right? That cats have become not evil at that point in time. It's in the Bible. So if I want to make use, basically I'm looking for some kind of expansion of the function about z naught, right? So what do I do? In order to make z centered at z naught, I add and subtract z naught. So I can say, okay, so that's w minus z naught minus parentheses z minus z naught. You're like, but you subtracted z naught 2 times. Well, no, I didn't, because I added z naught in the second term, right? But we can rewrite this as what? This is really f of w, well, f of w over w minus z naught times 1 over what? Times 1 over 1 minus z naught over w minus z naught. Well, isn't that convenient? Because that is precisely 1 over 1 minus, something, where that something has modulus less than 1, right? So what can we do? The same thing we do every night, try to take over the world? No, that is not the answer. Let's see here. The answer is to use the geometric series with the radius of z minus z naught over w minus z naught, which we know we can do because of the preconditions, forcing that radius to be modulus less than 1, right? So this is the sum k equals 0 to infinity of z minus z naught over w minus z naught to the kth power. Geometric series result we proved earlier, right? But we can clean this up a little bit more, right? What is this actually equal to then? Sum k equals 0 to infinity of f of w over w minus z naught to the what? To the k plus 1 times z minus z naught to the k. Okay, there we go. That's a pretty nice formula for f of w over w minus c. You got it all, Sharon? Okay. I'm worried she may be exacting her revenge after my homemaking commentary at the start of class. I hope you wouldn't let the math suffer, just because of our own personal differences. Let's see here. I'm sure that won't happen. Okay, so f of z is well, how about this? It's 1 over 2 pi I, right? Integral over modulus of w minus z naught equals to r, and in the usual counterclockwise fashion, right? Of what? What did we prove we can represent f of z by? If f is holomorphic inside this circle, which we're assuming it is. How about f of w over w minus c, right? Something I should have emphasized over here is not only that we have this geometric series result, but that this uniformly converges, right, on the circle. Right? It's a uniformly convergent series. So I can take that representation of this quotient, right, and I can stick it in there. And then what can I do? Integrate term by, right, I can flip the order of integration and summation because we have uniform convergence, right? And we know that the sequence of the integrals is the integral of the sequence for a uniformly convergent sequence of functions. So I'll just go ahead and do that. So plugging that into here and flipping the order of integration and summation, I have the sum k equals 0 to infinity, 1 over 2 pi I, the integral of over w minus z naught equals to r of f of w dw over w minus z naught to the k plus 1 power, right? And then all of that times z minus z naught to the k. Again, using the uniform convergence of the series to flip the order of integration and summation. But that's exactly what we wanted to prove. This shows that f of z is in fact analytic, right? What are the coefficients in the power series? What are the quote-unquote a sub k's? This whole thing is a sub k, right? Ignoring the z minus z naught to the kth power. So think about this. Put yourself in the shoes of Cauchy, perhaps. You found Cauchy's integral formula, right? You know about analytic functions because Lagrange wrote this book on calculus where he assumed every function was analytic in 1780. So like Lagrange is like, suppose f is a function, so f of x is equal to like a constant plus x squared plus coefficient times x cubed plus dot dot. I mean, like he assumes analyticity in his definition of function, right? So Cauchy was certainly aware of that concept. So if Cauchy found Cauchy's integral formula like this, then he would immediately find the generalized integral formula by this calculation, the so-called Cauchy kernel. And we already know by Taylor's theorem that this is equal to what? The kth derivative at z naught divided by k factorial, right? So we find kind of an alternative way of understanding where Cauchy's generalized integral formula comes from. Before we just did differentiation under the integral, or that inductive argument that I didn't do in class. But any questions? Partly the reason I'm showing you this proof is it kind of ties things together. You see how we get to use uniform convergence, right? We get to use most of the theorems we've been working on the last few weeks. But also this calculation at the start of it, the algebraic underpinning of this argument is something we do again and again and again in examples. This trick here. It's worth thinking about. All right, well that's it for that. I'll move on here. The corollary to this theorem is what? There's a few corollaries. What do you think we can say if we have two holomorphic functions? Suppose f and g are holomorphic on D, then if the kth derivative at z naught of f is equal to the kth derivative of g at z naught for some z naught in D, then what? I mean, the corollary is actually stated for this D is actually, more specifically, it's modulus of z minus z naught less than r. But in fact, I think this equally well applies for an arbitrary domain if you have matching coefficients. I think that's still true. But the proof I have in my notes is really just for a disk, so let me not be too greedy. Then what can we say? In other words, you have all the derivatives matching at one point, then what happens? What's the conclusion? Blank equals blank. Yes. Thank you. Then the next corollary, and I'm actually going to use that corollary, 5.4.3, for some of the examples that follow here today. But the takeaway message from all of this is really contained in corollary 5.44, which simply says this, that if f is analytic at z naught, what do we mean analytic at z naught? Right, that means that there is some open neighborhood, at least, on which on which f has a power series which represents it, right? I think I need at least an open, like just at z0 alone is not enough, because you can always just take the constant series f of z0 itself, and that doesn't really give you any information about f per se. F could behave very badly close to such a point. Anyway, f is analytic at z0 with power series expansion centered at z0. A sub k, z minus z0 to the k. Then the radius of convergence of the power series is the largest number r such that f of z extends to be holomorphic on the disk. Is the largest number for which f of z is holomorphic on the disk z such that z minus z0 is less than r. All right? And that power series converges normally on the disk of convergence, all right? All right, so the next few examples I have, pretty concrete. And the issue we're about to face here is a war of definition, right? So we're in the midst of a political campaign, right? You have warring definitions, like one person wants to define the Republican Party one way, one person wants to define the Democrat Party a different way. Everybody's got their own pet idea of what these political parties should become. Well, we're kind of dealing with a similar issue here, except mathematically. So the first example deals with the question, what's the exponential function? Like, how should you define the exponential function in the complex domain? How did we define it up till now? What was our definition? We had what? E to the z was what?
E to the x times d cat y, or e to the I.
Right. Right. E to the x times cosine of y plus I sine y. Right. So let me call this f1 of z. Well, let me just call it f of z. How about that? Now let's look at g of z. Oh, by the way, this function is what? It's entire, right? In other words, f is an element of the holomorphic functions on the whole complex plane, right? Take complex derivatives wherever you want, and this is the one that's pretty hard to mess up, right? I mean, derivative e to the z is what? Okay, we know. It's e to the z. Surprise, surprise. How about this? G of z, I'm going to make up a new function. The sum, k equals 0 to infinity, of z to the k over k factorial. In other words, it's 1 plus z plus 1/2 z squared plus 1/6 z cubed plus da-da-da. I'm defining g by this power series. What's the radius of convergence for the power series? Let's see, what's the kth term? A sub k is what? It's 1 over k factorial, right? So we could use the ratio test. What did the ratio test say look at? Modulus of, what was it, ak over ak plus 1? I can't remember, guys. You have to help me out. I think it, or was it the other way around? The ratio of this limits to the radius of convergence, right? Is that right? Okay. I'll trust you. Don't let me down. So this is k plus 1 factorial. I mean, 50-50, I'm right. Or wrong. So it's k plus 1 factorial over k factorial, which is what? K plus 1. This goes to infinity, right? So in other words, the radius of convergence for the series which defines G is infinity. Hence, G of Z, well, more to the point, the sum k equals 0 to infinity of z to the k over k factorial converges on C, right? The radius of convergence is equal to infinity. Okay? So the function f and the function g are what? They are both holomorphic on the entire complex plane. Are they the same function? Well, we can use corollary 5.4.3 and check, right? What is f of 0? Well, I guess one more thing. We already know that we've previously proved that the kth derivative of f of z is just equal to f of z again, right? I guess it remains to show that g of z is also having this property, right? So what's g prime of z? 1 plus z plus 1/2, well, 2 over 3 factorial z squared plus da da da, right? In other words, it's g of z again. Or I could be more careful and do this. If you differentiate z to the k over k factorial with respect to z, you get k times z to the k minus 1. But k over k factorial is 1 over k minus 1 factorial, so we get z to the k minus 1 over k minus 1 factorial. The k equals 0 term is 0. We restart the summation at k equals to 1, and we get back the exponential series, if you want me to be more rigorous. And why can we flip the derivative inside the integral, inside the series, is, well, we've just proved it's holomorphic on the entire complex plane, hence it's uniformly convergent on any open disk, closed disk. It's normally convergent, in fact, on the complex plane. So I'm certainly entitled to do this calculation. There it is. Okay, so check it out, right? What's the kth derivative at 0? Is just what? It's e to the 0. But the kth derivative of g at 0 is just, well, plug in 0, right? 1 plus 0 plus da 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 equals 1, right? Which is equal to e to the 0. Consequently, these are the same functions. So what's the definition of the exponential function? Whichever one you like. They're equivalent, right? Although, of course, this does beg the question, how did I know what the real exponential was, right? So logically speaking, the g of z definition should be primary because it's completely self-contained. It makes no reference to outside math except for the convergence of series, which we have developed. So this is a nice, rather logically complete definition for the exponential, which, by the way, will reproduce the real exponential when you restrict it to the real line. Any questions? Shall we play this game again, but with another function? Let's do it. My next example is Cosh, I think. Can I erase? Okay. So I'll just kind of list them. You could say Cosh of z. Well, we had our previous definition was 1/2 e to the z plus e to the minus z, right? Versus the Cosh of z is the sum k equals 0 to infinity of 1 over 2k parentheses factorial z to the 2k. You could contrast sinh of z defined by 1/2 e to the z minus e to the minus z versus sinh of z is the sum k equals 0 to infinity of 1 over 2k plus 1, parentheses factorial, z to the 2k plus 1. There are different ways of understanding the relation between these series. I mean, one thing you could do would be this. You could just say, okay, well, on this side, I have that e to the z is cosh of z plus the sinh of z, right? But on the flip side, it's also equal to what? You know, the sum k equals 0 to infinity of, well, let me say j equals 0 to infinity of z to the j over j factorial, right? Because of what the example I just did. But then that series has either even terms or odd terms, right? And it's easy. You guys can check this out. If you have an even function of z, it must have just even powers in the power series expansion. If you have an odd function of z, it just has odd powers in the power series expansion. So by comparing even and odd powers and the fact that cosh is even and sinh is odd, you could also immediately derive from the exponential that the hyperbolic cosine has to be all the even terms in the exponential series, which would be these guys, whereas the hyperbolic sinh has to be all the odd terms in the exponential series, which would be these guys. That's another way you could come to derive these formulas. But again, we could go back and be boring and just use the same argument we just did and show that the derivatives of the series on the right match the functions on the left for both of these. Anyway, you should know these series for our future reference, okay? We can play the same game with complex sine and cosine, right? Let's see here. What's the deal? I'll do it over here. So we have cosine of z. We can define it in terms of power series to be the sum k equals 0 to infinity minus 1 to the k over 2k parentheses factorial z to the 2k, so that's 1 minus z squared plus 1 over 4 factorial z to the 4th plus da-da-da-da. And likewise, sine z is the sum. It's like the same as sinh, but there's a minus, there's an alternating factor, right? K equals 0 to infinity minus 1 to the k over 2k plus 1 factorial z to the 2k plus 1. Of course, you could see these, right? You could see these popping out of the imaginary exponential extended to the complex domain, right? So like, if we take Euler's identity and extend it to the complex plane, so like e to the iz is cosine of z plus I sine z, right? A lot of the time we've played with that identity where z was like a real quantity or a pure imaginary quantity or something, but it's in fact true for complex quantity. And so if you expand e to the iz in a power series, basically substitute iz into the exponential series that we looked at earlier, what do you get? You get sum k equals 0 to infinity iz squared over 2k factorial plus the sum k equals 0 to infinity iz, to the squared, I don't mean square, what do I mean? Iz to the what? To the 2k power. And over here, iz to the 2k plus 1 power. So what did I do? I just split the exponential series for the exponential of iz into two pieces, the even and odd pieces. What is I to the 2k equal to? You say what? Minus 1 to the k, right? So let's see, let's think about that. I to the 2k is equal to I squared to the k, which is minus 1 to the k. So that's why minus 1 to the k here. I to the 2k plus 1 then is equal to I times minus 1 to the k. So that gives me an extra factor of I, which I pull out. And I've got the sum k equals 0 to infinity, minus 1 to the k over 2k plus 1 factorial, and then odd powers of z, right? Z to the 2k plus 1. So then again, you can compare the even and odd functions on either side and so derive that the power series expansion for cosine must be this term here, and the power series for sine must be this term here. I mean, there's a lot of different ways you could come at these relations and interrelations. It's a chicken and egg kind of story, right? What do you take as basic? So don't get too wrapped up in trying to understand what I'm doing until you're sure, you're absolutely sure what you've taken is basic, right? Once you've made that decision, then you can analyze whether or not my argument makes sense to you. Otherwise, I'm just showing you some results which are consistent, okay? So what should we take as the definition of complex sine and complex cosine? You have choices, right? But I personally think that the most logically complete choice that requires as little, let's say, phone a friend kind of stuff is this. I mean, this is sine of z. This is cosine of z, right? And you can prove that these series are entire by the ratio test. It's like a line. It's essentially the same as what we just did. You can prove the radius of convergence of this is infinity. You can prove the radius of convergence of that is infinity just by a simple one-line ratio test. So there you go. Sine and cosine are defined on the whole complex plane by these power series. It's then a straightforward business to prove all the usual properties of sine and cosine. It's not hard to prove sine squared plus cosine squared is 1, for example, using series arguments. That can be done. And lots of other things. Derivative of sine is cosine. Derivative of cosine is minus sine. These are all easy things to derive from the series definition. So anyway, enough of that. So we know we have our examples. Now we can work with them. We can do interesting, fun new things, right? Before I get to interesting, fun new things, I am obliged to tell you a word or two about power series expansions at infinity, which is a really weird idea. So I brought a manipulative to illustrate this idea. So it's like that. This is like at infinity, at a finite point, at a finite point, at a finite point, at a finite point. Infinity. It's like it turned inside out, right? So instead of looking, what are the domains to understand analytic at a finite point, understand analytic at a finite point, we're talking about a disk of convergence, right? So analyticity at infinity is kind of an odd duck. It's a little bit different. I won't spend too long on this. You should read this section. I'll just show you the definition and an example or two. A function f of z is analytic at infinity if the corresponding reciprocal function, g of w, which is defined to be f of 1 over w, is analytic where? At 0. What is it? What have I done?
Mine is guilty.
Wow.
I got her on the video though. We're good.
You're quiet. You could murder me in my sleep. Probably send an animal to do it though. So I have some examples in here. The ultimate result is there's a theorem, and the theorem 5.57 says this: if f is analytic at infinity, then there exists some radius rho greater than 0 such that for modulus of z minus z naught greater than rho, we have f of z is equal to a sum k equals minus infinity to 0 of a sub k times z minus z naught to the k. All right, and what that looks like is a sub naught plus a sub minus 1 z minus z naught plus a sub, oop, that's a typo, a sub minus 2, I got a minus 1 there, that's a typo, z minus z naught squared plus dot dot dot. So this is, if you have, if f is analytic at infinity, it has an expansion that looks like that on some exterior domain. In other words, an annulus which goes to infinity. Now, this is interesting. In foreshadowing to the next chapter, this is what's called the Laurent series. If you have a series of reciprocal powers, it's a so-called Laurent series. Okay. Just to give you one example, two maybe. If I have f of z is equal to, say, z to the fourth plus 3z squared minus 7, is this analytic at infinity? What do you have to do to figure out whether or not that function's analytic at infinity? What do you do? Well, you're like, well, you just wrote the theorem above, so I can, intuition tells me if f was analytic at infinity, I can expand that polynomial as a sum of reciprocals in 1 over z. That seems unlikely. So no. Okay, that's true. That's not the argument I'm looking for, though. So what we do is we look at the reciprocal function, right? G of w is f of 1 over w, which is what? 1 over w to the fourth plus 3 over w squared minus 7. And this is clearly not holomorphic where, well, not analytic, I should say. Not analytic at w equal to 0, right? So therefore, f is not analytic at infinity. What if we had something like this? F of z is equal to, say, z squared times e to the 1 over z. Is this analytic at infinity? So we look at f of w is what? F of w, excuse me, g of w rather. F of 1 over w, which gives me what? And then is that analytic at 0? Well, let's see here. No. That is not analytic at 0, right? Nope. G of w, not analytic at 0. W equal to 0. Therefore, f not analytic at infinity. Finally, one more example, and I'll stop with this infinity stuff. What if we looked at f of z 1 over, I don't know, z minus 1. I'll make it z over z minus 1 just for kicks. Is this analytic at infinity? So if I look at the g of w function, right? I have what? 1 over w over 1 over w minus 1. But this is actually what? 1 over 1 minus w, right? Which by the geometric series result is what? Sum k equals 0 to infinity of, well, w to the k. So indeed, this function is analytic at w equal to 0. And that implies then that f is analytic at infinity. Almost the same calculation will derive the Laurent series for f of z at infinity. So like basically go through the same steps as I just went through for the function. What do you have? Like f of z is equal to what? 1 over 1 minus 1 over z, right? And so that is equal to a sum k equals 0 to infinity of 1 over z to the kth power. For what? What condition do I need? I need that the modulus of 1 over z is less than 1. But can you recognize what that really is? That's the modulus of z is greater than 1. In other words, if this is the unit disk, then I can't, anyway, you get the idea. Outside this circle, it's convergent, okay? To that so-called Laurent series. Okay, so series at infinity bring us into contact with the topic for the next chapter, which is Laurent series, all right? This brings us to section 5.6, which is on the manipulation of power series. So here I discuss how to multiply, divide, and of course add and subtract power series. And basically what's said in this section is pretty intuitive, pretty simple. In other words, you just multiply and divide like usual. Let me show you a really weird example, though. This example I'm fond of. And then maybe next class I'll prove. I mean, I should prove that the product of the series is given by Cochise product formula, but that's not fun to do in the remaining 5 minutes of today. So I'm going to show you the example, which I think is kind of interesting. Here it is. This is example 5.66. Again, I guess I'm putting the cart before the horse a little bit here. Don't worry, I'll construct the cart next time. If I wanted to multiply 1 plus z squared plus all right, times 1 minus z plus z squared plus what would that equal?
Wait, what is the pattern? Just the same, except it's not alternating.
Yeah, exactly. This one's alternating. That one's not. I mean,
well, you go plus though. Shouldn't that be?
Well, I mean, yeah, sure.
Okay.
If it's not clear, I can add another term, minus z cubed plus and plus z squared, z cubed rather. All right, so of course we can multiply. Now, what Cauchy's product theorem says basically is you just multiply order by order, collecting all the terms. So like using Cauchy's product theorem, I would get what? I get 1, right? And then what are the linear terms? Plus z minus z. Then what's the quadratic terms? I get looks like I get plus z squared minus z squared. And then what else do I get? I get plus z squared minus z squared, right? Depending on how you order the terms. There are 4 z squared terms, right? The 1 times z squared, the z times minus z. Are there just 3 terms?
Yeah.
Oh. 2 pluses? Okay, so sorry, I double counted. And how about z cubed? So I got plus z cubed. I mean, depending on how you're, I guess I'll say minus z cubed to start with. I'll start with the minus. Then z times plus c cubed, yeah. Minus c cubed. Oh, plus c cubed, yeah. Right? Or, right? Or do this. This is what? This is 1 over 1 minus z squared, right? This is 1 over 1 plus c, rather. Sorry, 1 minus c. 1 plus c, right? So this is 1 over 1 minus z squared, which is 1 plus z squared plus z to the 4th plus da 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 da. Okay, so there it is. Would you like to see more on this theme of jerk questions? Here's another jerky question. Calculate the product of 1 plus x plus 1/2 x squared plus da 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 times 1 minus 2x plus plus 2x squared minus 4/3 x cubed plus da da da. Now, since I told you it's a jerk question, you have a chance of figuring out what I'm doing. But let me show you what this what this is. This is e to the x. This is e to the minus 2x. Because minus 2 squared is 4, 4 over 2 is 2. And then minus 2 cubed is minus 8. Minus 8 over 6 is minus 4/3, and so forth. Now, you could debate me as to if that's enough for the pattern to be seen, and that's debatable, of course. But once you see the pattern, the answer is e to the minus x. which, of course, you could write as 1 minus x plus 1/2 x squared. Yeah. Yep, what? Depends on if I'm feeling like a jerk or not. I don't know. I don't know. Don't make me angry. You don't like me when I'm angry. Have you seen my car? Okay.
Do you have a bumper sticker?
I want to buy a bumper sticker. I don't have one yet, but I'm going to get one. This math is the only subject that counts. That's my plan. But
your car is not the one with the license plate, so it's factory, is it?
I'm not the owner of the factorate license plate. No.
Do you know who is?
Mary Beth Grayson, maybe? I know Sopranos is Z mod 2, I think, or something. Z mod 2Z, yeah. We used to conjecture that was some sort of statement about him dating, but I think it turned out to be wrong. It's a finite group of order 2.
Do you want me to turn the camera off?
No, it's fine. It's fine. If that was still in debate, I mean, then I wouldn't say it, but students were like, I don't know, I think maybe Dr. Soprano's dating somebody. Students have too much time on their hands. We need to give them more homework, apparently. All right, so I have more examples in section 5.6 and also how do you divide series. So I'll try to do those next time. And but hopefully I'll try to do that quickly. Maybe the first 20 minutes of class I'll spend on that. And hopefully we'll be into order of zeros and stuff at the end of class, which is an important topic. So anyway, thanks.